Okay. Hello, everyone. Welcome to my presentation. I'm Shahin Shamsabadi, third-year PhD student in CIS under supervision of Andra Cavallero. And today I will present semantic adversarial example for privacy protection. What I mean by privacy here is that when you take a photo in your phone and then you share it in the online social media, those photo sharing ones like Instagram, to get some feedback or likes from your friend. But you should know that there are some classifiers that automatically and routinely infer some information from your images that are shared. For example, they can understand the scene, the presence of the people, the relationship that they have, age, emotion, and even the clothing style without your consent. So the problem here is that how we can share our photo in the online social media, just share it with our friend and prevent those kind of automatic inference. So in this talk, I will give you a high-level overview of the two recent work that we've done in CVPR and ICASP this year: ColorFool, semantic adversarial colorization, and EdgeFool, an adversarial image enhancement filter. And we will see that how they can help us to protect the privacy. In these talks, we talk about the deep neural network for image classification, that you have an image which is represented by multiple pixels value between 0 to 255, for example. And then you feed it through the DNN classifier. And then the output is the label that you want to recognize. For example, in this case, is suit. And as you know, we trained the neural network based on the pairs of the images and labels. So now let's see that how we can mislead or fool this kind of deep neural network. To do that, we use the adversarial image. Adversarial image is an image which is intentionally computed to be misclassified. For example, in this slide, I will show you one. In the left, that is the suit image. When you feed it to the deep neural network, in this case, ResNet 50, residual neural network with 15 layers, it can recognize it as a suit. But when you add this carefully computed perturbation in the middle to the image in the left, you will get the image in the right that human still sees the suit in this image. But when you present it to the ResNet 50, it recognizes the suit image as a racket. So when we want to use the adversarial images, especially for the privacy protection prior to sharing the images, they should have three main properties. They should be unnoticeable, which means that the adversarial perturbation that we add in the image, it shouldn't distort the quality of the image because you want to share it with your friend. So you don't want to distort it. The adversarial images should be robust to defense framework that they apply those kind of denoising transformation that is common in social media, like JPEG compression or even quantization and median smoothing. So the robustness property, you can satisfy that if your adversarial images still can mislead the classifier in the presence of the defense filter. And another property is the transferability. Transferability means that you are generating adversarial images for a particular classifier that you have in your hand, and you see that. But still, those adversarial images should be transferable to other unseen classifier that we never know, but we should be still fooling them. If we look at the literature, in this slide, we can see the limitation of them based on these properties that I just explained. If they are unnoticeable, they are not transferable, and they are not robust, and vice versa. The reason behind this is mainly because that they ignore the content of the image, the semantic information that exists in the image, and they generate adversarial perturbation, as you can see in the first row, that are irrelevant to the content and semantic of the image. For example, FGSM is a high frequency noise that are not relevant to the content of the daisy. So to tackle these issues, we propose a black box content-based adversarial attack to generate natural looking adversarial images, as you can see in the images in the second row. By black box, I mean that our proposed attack, ColorFool, doesn't need any internal knowledge of the classifier. We don't need to know the parameters, the gradient, the loss. We just need to know the output of the classifier, which is the label. And ColorFool generate the low frequency perturbation that can address those issues. To do that, we first understand the semantics in the image, semantic region. By that, I mean the object. And then we categorize the object in two categories, sensitive and non-sensitive. Sensitive regions are those regions whose colors are important to human eyes. For example, we used to see them in some specific colors. For example, person, the color of the skin, vegetation, water, and sky, as you can see with different colors in these three examples. Instead, non-sensitive regions are those regions that human can see them in different kind of colors. So you can change the color in a variety of the range, like curtain, wall, and other things. So after understanding the semantic region, we change the color in the LAB space as opposed to RGB space. Because LAB space is more related to the human perception. And in LAB space, the color is represented separately from the brightness. The color is in A and B channel, as you can see in this figure. And then, for example, we change the color of the vegetation, which are grass or those things in the green area. And the water, sky, lake, all those family, waterfall in those blue area. And we do this color changing or color perturbation up to 1000 trial randomly until we mislead the classifier. And here I would like to show you some of the examples. These are the original images. And here there are the colorful images. As you can see, we could generate some natural looking adversarial images. Original images, colorful images. So can we do better than colorful? I mean, in terms of the visual quality. So for doing that, we propose the structure-aware adversarial perturbation that can enhance the detail in the image or the edge, as you can see in the second row. So here our adversarial perturbation that we add to the first row not only mislead the classifier, but also enhance your image. So you can use it prior to sharing it on Instagram. Hopefully you can prevent those kind of unwanted inference that are done in your images. I would like to explain how it works. So for enhancing selectively those edges that can help for misleading, we need to decompose the image to the details and the structure. A structure of the image here is the smooth region, IS, in this slide. So to do that, we train the fully convolutional neural network based on the image smoothing filter using a smoothing loss function. This smoothing loss function, LS, measures the difference between the learned smooth image, which is output of the FCNN, and the output of the image smoothing filter, which is here L0 image smoothing filter. And then we avoid changing the color. For doing that in the LAB space, we just enhance the L channel, which is the brightness of the image detail, and then combine it with the A and B channel, which are the color information of the original image, and then transfer back to the RGB, and we have our adversarial image I dot in the bottom right. So we have here a LA adversarial loss that try to minimize the score of the belonging your adversarial image to the same class as the original image. And we train this pipeline end to end using these two smoothing, LS, and adversarial LA loss function to generate the structure-aware adversarial perturbation that enhance the image while mislead the classifier and doesn't change the color. Here, I would like to show you some of the example. Original image, EdgeFool images. As you can see, the details are enhanced, and all of this example, they change the output of the classifier. The takeaway from my presentation is that if you would like to work on the images and design your machine learning algorithm, it's better to look at inside the images, the content and image semantic of the images, as we saw in the presentation that we had at 12. It's about Dinesh that said that they wisely select the view. So here, if you can wisely select the semantic information inside the image and design your attacks or adversarial images based on that, for example, you can take advantage of the structure, the detail, color of the image, and design your algorithm. So images are special data. And if you want to see more works on this topic and our code and demos, so you can check my website and feel free to ask me any question here or offline. Thank you very much for your attention.